So today we're going to be talking about high-speed autonomous driving with Autoware, ROS2, CycloneDDS. So I'm Joe Speed with ADLINK, here with my friend Tom.
Hello.
So we're both vehicle robot people. So for myself, I'm on the Open Robotics ROS2 Technical Steering Committee. I'm involved in Autoware, Open Autonomous Driving at Eclipse Foundation. Spent a lot of time around open source IoT, and actually while I was at IBM, I launched the IBM IoT and their Automotive Innovation Lab.
Great, thanks, Joe. So I'm Tom. I am a robot perception guy, a mobile robot perception guy to be specific, and even more specific, I would pass, I don't know, decade or so, been doing a ton of work with LiDARs and 3D LiDARs in particular. My current day job is at Seegrid, where I lead the perception team there. We do industrial vision-guided automated vehicles for warehouse applications. Prior to Seegrid, I had a startup called Box Robotics, and one of the many things we were doing at Box Robotics was working together with Joe and his team on effectively what we termed kind of renovating the LiDAR perception stack in ROS2. So some of the work that is going to be deployed to these vehicles was the work that we had a little bit of a hand
in. And it's hugely appreciated. So one of the things we'll talk about today is something that it's really this fellow's fault. Sebastian Thrun, who his team won the first DARPA Grand Challenge. So the way it was explained to me is that he was at the Indy 500 watching a race and made the comment that, you know, if this was autonomous, that would be really exciting. Like, I would watch that. And it's this that really gave birth to the Indy Autonomous Challenge, which is a program that we're involved in, which is a $1.5 million cash prize, $1 million first prize program of autonomous Indy cars, specifically Dallara IL-15, so Indy light vehicles, outfitted with sensor suite, autonomous driving system, drive-by-wire, and it's a university competition. So all of your favorite universities are involved. There's 39 universities with more joining all the time. And many of these teams have multiple universities collaborating together. And why autonomous racing? So for people who care about topics of autonomous driving, autonomous vehicles, mobile robots, all this, the autonomous racing, you know, motorsports racing has always been a great proving ground for automotive technology. And if the public can see these university developed autonomous race cars doing 170-mile-an-hour laps, 200-mile-an-hour top speeds at Indy Motor Speedway, that's going to go a long way towards building public trust in these things. And so what are some of the benefits of racing? You know, racing presents these close-in high-speed situations much more frequently than you find in regular traffic. And most crashes that you see in autonomy are failures of perception or of estimating the agent behaviors. And so what we're doing here is we're really working to develop so that these vehicles can steer aggressively and really learn expert-level maneuverability.
Great. So kind of wondering, you know, well, what is a warehouse robot guy doing with a race car robot guy? Well, what we're showing on the screen here is actually a live 3D reconstruction of an industrial facility that we did while at Box Robotics using an Ouster 3D LiDAR. What's happening here is that the robot in real time is creating a map of the environment, and this map is used for various perception tasks: localization, object recognition, obstacle detection, other types of things. Importantly for this discussion today is that this sensor stack that we're using in industrial environments is the same or similar to the stack that's going to be on these Indy race cars. Now, we're not driving at nearly the speed of an Indy race car when we're moving goods around a warehouse, but, you know, we have continual pressures in the industrial environment to move faster, have richer perception, operate more intelligently in general. So we're interested in what's going on in this Indy challenge to see, what core technologies are going to be developed by these teams that we could use to spin out and maybe think about embedding into a commercial product. Of particular interest, especially as it relates to the Indy cars, is speed. We're under pressure to have vehicles move faster and get more throughput. So if the algorithms that these teams can develop based on similar sensor stacks that we're employing today in the warehouse, we'd be real interested to see what could happen and how could they be applied to our applications.
And some of the work that Tom has done, you'll actually see it in these Indy cars. So as he's been working with the community to renovate this open source perception and robotics and autonomy stack to do more high performance use cases, this is giving a great basis for the universities to build upon. So in the Indy Autonomous Challenge, we're over a year out from the final race in October 2021, but we're already seeing some interesting results. So you've got a hackathon that we completed last month with all of the teams, with the winner turning in over 120-mile-an-hour laps of the Indy Motor Speedway in simulation. But something I thought was quite interesting is that not only did Polymove from the University in Milan turn in 120-mile-an-hour laps, so did 6 other university teams. And you look at, there's only a quarter second separating the lap times of the top 7 teams. So, this is very promising. I think we're really in for something special. And we're over a year out, but look at some of the press we're getting already. Wall Street Journal doing a first in a series article, Fortune, TechCrunch, Verge, those articles coming soon. And people like Automotive News, Robot Report, and Strategy Analytics looking at, what does it mean to have these open source autonomy stacks with the Autoware, the ROS2, the CycloneDDS. And this work that we'll do here, it's not just about Indy. So something that was a bit illuminating is discovering that these teams in the Indy Autonomous Challenge, that these teams are also involved in these other autonomous racing programs, and that's being used as an educational tool for them to learn about doing autonomous driving and high performance autonomous driving. So programs like F1TENTH, led by Medora at University of Virginia, Raul at UPenn, Venkat at Clemson University, and they're huge community people. EV Grand Prix run out of Purdue with one of my favorite teams, University of Hawaii, and what they're doing in that program. SAE Formula Student Driverless, which is good for about 75 miles per hour. So you go from F110 to keep climbing in the size and speed of the vehicle. So you go from F110 at maybe 25 to EV Grand Prix at 50 to SAE at 75, all the way up to Indy Autonomous Challenge, the Dallara race cars doing top speed of 200 miles an hour. In the stack that we work on to put together for these folks, you think of Autoware Foundation, Open Robotics, OpenCV, Eclipse Foundation, all of these open source foundations coming together to support the programs and help the teams, and delivering a software stack of Autoware Auto with perception, a lot of contribution that will be coming from Gary Bradsky and his team at OpenCV for the perception pipelines, with ROS2 from Open Robotics, so ROS2 Foxy, and then the Eclipse Foundation middleware, so the OpenADx technologies of the Eclipse CycloneDDS middleware, with the Acerics zero-copy shared memory pub sub implementation, with Zeno providing the V2V, V2X, and V2Cloud capabilities here. Tom?
Yeah, so I mean, the interesting thing here is that these same technologies are technologies that are being used in industry as well. And so we did a bunch of work on the ROS2 Ouster LiDAR pipeline. Our focus over the summer was shaking out the jitter in that. So these point clouds, from a data structures perspective, this is a lot of data getting pushed through this many layered cake that, is fueling the perception systems. We did a bit of work with kind of reorganizing the data structures in memory in such a way that the algorithms that operate over the pixels in real time could do them more efficiently, more naturally as to how a computer vision person would expect to see them, as well as leveraging the caching machinery of the computers themselves. One of the things that we're really excited to have come out of this work is the integration of Acerics with the Cyclone from a robotics architecture perspective. You typically separate out different pieces of your software into actual running processes on the usually Linux system. And for compute nodes that are, and when we say compute node, think of that kind of maps to like a Unix process for this discussion. They're sharing data on the same machine. And what Acerics gives us is a way to share data between processes without copying that data. So a side benefit of this whole race and all this work that's going into all this open source infrastructure is that everybody's going to benefit from these kind of high performance software systems that'll be rolled out to the public.
Absolutely. I'm a car guy. I spent a lot of time in automotive, and what I've began to understand is this is not an autonomous vehicle, autonomous car topic. This is an autonomous driving topic. And autonomous driving spans from an iRobot Roomba all the way to a vehicle on the highway. And all of these things drive, and they share much of the same stack. So, it's great to see, like, when iRobot does an upstream contribution of something that improves the performance and reliability on their robots and vacuums, that ripples all the way through, and the next day you see that benefit in the vehicles that use that stack. So it's all very connected. So the things that we do with universities, the kinds of performance stress testing optimizations that we'll do, you'll see that just rippling through the whole ecosystem. So these pieces that we're talking about, Autoware Foundation is an open source nonprofit around self-driving and self-driving mobility. So in the stack, we're using Autoware Auto, which is a set of packages for autonomous driving in ROS 2. OpenCV, as I mentioned, Gary Bradsky and his team doing contribution around this. So quite excited about what we can do with that. And one of the things that might be able to take some advantage is that we're actually going to be outfitting the vehicles. Originally, it was designed with 5 cameras, including 1 forward-facing. We are actually going to be putting 2 forward-facing, so we can do some interesting stereo vision things in these race cars. And we're definitely going to need a high-performance pipeline. So whether you're talking about the LiDAR or the cameras, these are vehicles that travel at 89 meters per second top speed, which is, slightly faster than your average forklift.
Just a little.
The human-driven forklift, what's that good for in the factory?
Human-driven forklifts, they typically would drive anywhere, I would say, 5 meters per second, maybe a little faster than that.
Yes. So slightly faster.
Yeah.
The also all of this running, of course, with the ROS 2, robot operating system, which is neither a robot nor an operating system, but is tools and framework for developing robotics applications. And if you were ever wondering, when could I adopt ROS 2? With the release we had this past summer of ROS 2 Foxy, now is the time, right? It's a huge effort, a lot of engineers, a lot of contribution, and really gives us a great basis for building this autonomous driving stack. And this is one that you've been spending a lot of time on.
That's right. Yeah. I mean, if anybody watching this presentation needs further validation, I would say if you're on the fence, now is the time. Jump to ROS 2, install Foxy, it's a productive environment, and I think anybody that's kind of doing ROS today is very, very, if they're not already there, they're very critically thinking about how they're going to get there.
Mm-hmm. And the fact that we had the very last ROS Classic, ROS 1 release, Noetic, if that's not a clear enough signal that you should start looking at migrating, I don't know what is.
That's right.
And then this running with the Eclipse Foundation technology. So Eclipse Foundation, they do a number of things. The one where myself and others I work with spend the most time is around the Internet of Things technologies. So you've got the Eclipse IoT program, which is a result of some initial seed contribution of the MQTT source code and funding that I helped bring about. And you've got the OpenADx, the Open Autonomous Driving Working Group. And these two, they have some key technologies here, the CycloneDDS, the Acerics, the Zeno, and take a look at some of those. So Cyclone, what is that? It's a easy, fast, small, reliable DDS implementation. It's taking everything that we've learned from our, I don't know, something like 150 man years of DDS experience at my company and doing a next generation implementation. It's built into Open Robotics ROS 2. It is the default for autonomous driving developers and Autoware Foundation. And Open Robotics and the ROS 2 TSC are evaluating it to decide if it should become the new default for ROS 2. And this is something that you've spent a lot of time working with, Tom.
That's right. Yeah, at Box Robotics, our default absolutely was Cyclone. It was kind of the base set of settings that Cyclone ships with works for the majority of applications, and for those that we needed to tune, it was very straightforward to do from a execution standpoint on the physical machines. And I think just as importantly, at least to us as a commercial entity, was the accessibility and availability of the team. ADLINK and the Eclipse developers themselves were there to support us, and they were genuinely interested in kind of seeing their technology out there, but also kind of learning from the applications of what we were trying to apply it to and try to make it work.
Appreciate that. And these are the people he's talking about. So these are contributors to Eclipse CycloneDDS. And if you work in open robotics, you of course recognize a lot of these faces here. And they really go to a lot of lengths to try to understand what people's use cases are, and then figure out how to make it work and work well just out of the box for most people's use cases, which is not as easy as it sounds, right? Because one person is doing like a very high frequency control loops, someone else is doing images, someone else is doing point clouds, another person's doing a lot with Wi-Fi, and so this has really taken a lot of thought, a lot of development. And you see some of the result of that in who are the contributors, who are the adopters of this. So, a lot of names that you'll recognize here. Tom's company as well, which has been acquired. Congratulations.
Thank you.
So a lot of folks in a lot of different spaces with a lot of different use cases. And the Acerics. And Tom, you were talking a little bit about what this means to you.
Yeah. So Acerics, I have been very interested in Acerics since I first heard of it. So let me take a step back and just to make sure that we're clear on how this what it provides. So the compute paradigm in any ROS system is effectively a directed graph, okay, and like a directed data flow graph. And so you can imagine that the nodes in this graph are some piece of computation, and the edges connecting the nodes are like a strongly typed piece of data flowing from one to the other. It's a directed graph. So traditionally, what people do is each one of those nodes in this graph maps to, you could think of it as mapping to a Unix process. That's not entirely true with ROS 2, but for purposes of this discussion, it's a good enough mental model. turns out that, and so what's nice about this kind of process-based approach is that it's inherently distributed, right? Whether two processes are coexisting on the same machine or across two different machines, it's almost nothing to do to make that work in terms of designing your system. However, the practical matter is in many robots today, it's a single computer running this graph and kind of controlling the machine. When you're running multiple processes on the same machine, we take this overhead hit in serializing our data, traversing the network stack, traversing the network stack again to get it into the other process, and deserializing it, and then doing some work on that data. ROS 1 had this idea of something called a nodelet, which is basically gives you the abstraction of these nodes or processes, but all in the same process and communicated via threads. And ROS 2 has a similar idea through its component abstraction. These are okay, but your process is still all tied together. And what we really want to do is to take advantage of separate processes, but not pay the cost we're paying to pass the data between processes. And this is where Acerics comes in. Acerics gives us that same pub/sub abstraction that we like when we talk across process boundaries, except it does it in a shared memory style so that we no longer have to pay all that overhead cost of serializing, pushing bytes around, deserializing, and just adding latency to the system. And you can imagine when we're talking about 200 mile an hour, 120 mile an hour Indy race cars, all of this matters. So, and it matters for vehicles I work on too, which are much slower. We're always looking to lower latency in our systems.
So on the IAC race car at top speed, you know, if you're 20 hertz Ouster LiDAR, you're talking about a new point cloud every 4.5 meters.
Right.
So anything we can do to speed up the pipeline on that.
Yep.
And another project here, the Eclipse Zeno. So this is a sister project of the Acerics, of the Cyclone. And this does quite a few things. So it's a ROS2 DDS bridge, and it gives you scalable discovery. So think about being able to have scalable fault-tolerant discovery with need-to-know discovery. So endpoint matching, which can really do a lot to reduce the chattiness, how much load there is on the network, and how much memory it's using in each of the systems within the network. You can enable swarms, you can do V2V, V2X, V2Cloud, all these kinds of things. And so for doing like ROS2 DDS bridging to cloud, what we've seen in our own testing is like 2 orders magnitude higher performance than using commercial DDS bridges. So think about running this on LTE, 5G, LoRa satellite, all the wireless. This is some technology that's already going into 5G base stations in Europe for cloud robotics and other kinds of initiatives. And it's quite fast, quite performant. So here with a pair of systems and a 10 gig E network, we're able to saturate a 10 gig E network with messages as small as 1 kilobyte. And it also supports microcontrollers. We have this running down as small as 8-bit Atmel microcontrollers, and we will be releasing a drop-in support for micro-ROS, so a RMW Zeno for micro-ROS as well. Would love all of you to go learn more about these things. You know, how do you work with the LiDAR? How do you work with the ROS2, the DDS? How do you do perception? How you do autonomous driving? So a lot of us have gotten together and developed a free 14-course series that you can learn to go do these things. And here's a few more links for you so that you can go deeper on all of these topics. And this is us, you know, encourage you all to reach out, connect with us. Tom, any closing thoughts?
Yeah, I would just say, I will echo what you said, Joe. Please reach out. if you want to learn more, we're friendly guys and always up for a conversation about autonomous driving at speed.
Absolutely. See you all on the racetrack.
Take care. Okay, so Joe is not available right now to help field these questions, so I will do my best to field all of them. So I have the first question in the chat, and I'll read it for the benefit of everybody. It says, you use quite some software frameworks. Where are the major challenges in integration of these? Are you working on some kind of best practices for integrating these into a tool chain or so? Yeah, so that's a great question. I think really it all gets integrated in the ROS 2 framework. There's a ton of extensive documentation on the ROS website. But really, at the end of the day, all the way up from integrating all the packages, building all the packages in a consistent way. Like, for example, in ROS, at the lower levels, it's primarily CMake, but there's a higher level, like, kind of driver tool called Colcon that kind of is this unified way to build out all the packages, and you can kind of pick and choose how to incrementally build things. ROS has put into place as well kind of best practices around CI/CD, even at the unit level testing, things like this. So ROS is not new, right? I mean, this has been around for well over a decade now. A lot of lessons learned, a lot of kind of battle tested approaches to kind of doing robotics in this way. So I guess that would be my answer to that question. Next question. Okay. Now that we have a chance to get insider information, on which team should we bet in the Indy Autonomous Challenge? I am not going to make any statements there, and I guess you'd want to talk to Joe about that. Okay, I don't think we have any other questions. Thank you.